Now this is a little snip from a virtual reality video game. This is a giant bird that's chasing me and trying to eat me, and I'm flying away from it. Now it's cornered me and it's coming towards me, and now it's eaten me. But luckily I have a vortex gun, so I can blast it. So it's not too hard to imagine other video games of this sort with a cheap consumer virtual reality system. Now here's something that's not cheap. It's a 6 degree of freedom force feedback arm that can deliver forces and torques to the user's hand. This is an early demonstration that we could integrate forces, visuals, and sound into the same system. Now moving again 3 years into the future to 1993, we have again another generation of graphics engine, this time Pixelplanes 5, which can deliver much more sophisticated and complex graphics in real time, 2 million polygons per second is the spec. And if you can remember the other house interior, this is going at video rates, and it's also much more complicated. You can see there's a texture on the ceiling, and take note of the wood texture as we go past this wall. It's a much greater image complexity than we had in the earlier system. Now this is a demonstration of a program called 3DM that's for 3D modeler. It lets you, within the virtual world, construct three-dimensional objects. It's a modeler. So there the user used that palette, Macintosh style palette, to select a cylinder, and now he's using a selection tool to select the top surface of the cylinder. Little spheres appear around each of the points in that surface, and now he's going to scale that up to make it more of a more conical. And now he's selected a color, green. Now he's going to draw a few leaves coming out. So this is a flower pot with a few polygonal leaves that are sticking out of it. So in just about a minute, he's created a fairly complex little model there. Now we're going to look at another application of the virtual reality hardware and software at UNC. This project is called the Nano Manipulator. It's a virtual reality interface to a scanning tunneling microscope. So here the user is flying over a surface that's been scanned in from a sample down beneath the microscope. Now he's scaled the virtual world representation of that surface down till it's just a meter across in front of him, and he's grabbed it and he's tilting it from side to side to use the simulated light source highlights to try and see the contours of the surface. Now this box that's being opened up here is the box that contains the scanning tunneling microscope itself. The microscope needs to be isolated vibrationally and electrically and thermally, and that's the purpose of the box and the suspension tripod there. You can also see a little sandwich of metal and rubber that's part of the vibration isolation. And now we're getting closer to the business part of the scanning tunneling microscope, but it's hard to see what's going on. But there's a tiny little wire, a probe, that sticks in close to the sample, and that's what's used to measure the height at various points. And this is the wire, very thin. Now we're back in the virtual world, and we can see the data coming in real time from the scanning tunneling microscope and updating the virtual world model. So that little line sweeping across there, those are the actual new samples coming in from the microscope. Now here's another a set of data that's been scanned in from the scanning tunneling microscope, this time at atomic resolution. So each of those red ridges is a bond between carbon atoms and graphite. And what we're going to do here is use bias pulses from the STM tip to modify the surface. So we've scanned a region there. Now we've reduced the scan to a smaller region, and we fired a bias pulse, and you can see that a little hill appeared there in the surface. So we actually modified the surface. The surface is gold, and we've got a gold wire, a gold tip. So we've basically deposited a little blob of gold onto what formerly was a flat surface. And now we're going to, we fired 2 pulses actually, so now we're going to switch back to scanning the entire region we started with. And if you can remember, it was rather flat when we started, and now as we rescan, we'll see that some bumps appeared, showing that we actually did modify the surface down there. That bump is about 50 nanometers across.